Okay, you guys, right now we are going to talk about ionization energy in a little bit more detail to make sure that we understand how it works and what it means, because it's going to give us the ability to more appropriately predict how atoms and elements are going to behave. All right, so just a little recap. We talked about ionization energy when we were talking about periodic trends, but just to review, first, ionization energy is the energy required to remove the easiest electron from an atom, which creates a 1+ cation. So if you were going to look at this image that I have on the right side of the screen, this is an atom. I've depicted it as the Bohr model. As you know, if we depict it as the actual shapes of the orbitals, it's utter chaos. And these depictions mathematically really closely resemble what's going on. So it's kind of slick. Anyway, where do you think, if you were going to pluck the first electron off of this thing, which one would you take? Would you take it from the 1s? Would you take it from the 3s? What would make sense to you? So hopefully it makes some sense to you that we would take this from the 3s because they're vulnerable. They're out on the outside of the atom. There's all these other energy levels that you would have to get through if you wanted to try to take the 2s or the 1s or something like that. And so if we're going to lose an electron, it's going to get lost off of that valence ring or valence energy level. So once we've taken that first one off, and it could be either of these with the red arrows, it could be either of those electrons in the 3s orbital, what do you think a second ionization energy might be? So we know first ionization energy is the energy to take the first electron to make a cation. What do you think second ionization energy might mean? Second ionization energy is the energy required to remove the second easiest electron from the atom, creating a 2+ cation. So you already took one electron away, and so I put that little hole with the little dashed line. Right, so we snatched that electron out of there. We could have taken the bottom one. I just took the top one because I did. Second ionization energy says, okay, well, now let's take the bottom one. So now we would have taken both of the electrons out of the 3s orbital. And so basically then, this atom is just left with the valence of 2p6, or a valence of 8 if you want to count your 2s orbital, which you definitely can, and perhaps even should. So now my question for y'all is, do you think it's harder or easier to remove the first electron or the second electron? Which one do you think's harder to remove? It takes more energy to pull that guy off. So to discuss this in a little more detail, let's look at an example. So the atom that we've been looking at, in my estimation at least, this is magnesium. So we took the first one off the top, and then we took the second one, and usually it's, well, not usually, it's always a little bit harder to take the second one. Always, right? Because the electrons are being held right, and attracted by the nucleus. We've got 12 magnets in the nucleus attracting the electrons, and so these 12 protons are trying to hold on to 12 electrons. And if you take one of those electrons and it only has 11, it can hold on to the 11 it has a little bit tighter. Okay, so then something kind of interesting happens. So we can see it's a little bit harder to take the second one. But then if we wanted to take a third one, so here's the third one, it could be any, right? It could be any of these in the 2p6. I just picked this one totally randomly. So if you want to take that third one, what we notice in this graph of the data is actually this really big jump in ionization energy. We had kind of a little bit of an increase. It's a little bit harder to take the second one, but it's a lot harder to take the third one. But then after that, it kind of evens back out as you're taking more and more. It's getting harder, right? But it's kind of getting harder at the same rate. Like it's getting a little harder, a little harder, a little harder. Whereas down here, 2 to 3, it's like a lot harder. So why do you think that is? Why do you think there's such a big jump in energy between the second and third ionization? So the reason for this is because we've dropped a principal energy level. Our third electron is physically closer to the nucleus, and it experiences less shielding, right? So the nucleus can hold on to it a little stronger. And at this point, the atom is kind of energetically stable because it's got that full octet. It's got a full 2p6 rounding out its second energy level. So it's really stable. So it really does not want to give up that third electron. But then we can see after that, it's kind of like, all right, it's getting harder, but it's not like all of a sudden like, whoa, this is crazy. It's so much harder. But that is going to happen again. We're going to see a big jump again. Try to make a prediction. Which two ionizations, so it's going to be 8 to 9 or 9 to 10 or whatever, which ones do you think would be another big jump? We know that, 3, 4, 5, 6, 7, 8 is all kind of an even increase. And so where do you think we might see another big jump? We would see a big jump when we drop down to the 2s orbital, right? We drop down and we're even closer to the nucleus. And now we have 12 magnets holding on to 4 magnets. They're going to be able to hold on really tight. So I would anticipate that 9th ionization energy is like way the freak up here, like, woo, that's really hard. You're probably not getting that electron off of that atom. That's what I would predict. So a way that we can kind of understand this is by something that's called effective nuclear charge. Effective nuclear charge is a way of saying, okay, well, we know our magnet is strong. It has a charge of 12 plus, but the charge of 12 plus is experienced by the electrons right next to the nucleus, but then we have that shielding we've talked about. So by the time you get to the outer orbitals, the electrons aren't experiencing that 12 plus magnet anymore. They're experiencing a magnet that's not as strong because of the shielding. And we can actually conceptualize this nicely using numbers. If you're a numbers person, this is for you. You're welcome. So effective nuclear charge is the net positive charge experienced by an electron in a multi-electron atom. And you're kind of like, what does that mean? So let's talk about what that means. It depends on two things. Of course, how strong is the nucleus, right? If you have more protons in your nucleus, you're stronger. Easy peasy. More magnets equals stronger. The other thing it depends on is how many electrons are between the nucleus and the electron that we're looking at. That's shielding, right? So how many electrons are in the way, kind of interfering with the effectiveness of the magnet? So we can look at our little example of magnesium again and start to work this out. So here's my drawing of magnesium. And in the middle, I'll just label it so we know what we're talking about. Magnesium is number 12 on the periodic table. It has 12 protons. So it has a magnet of positive 12. Here's our orbitals. We've already had a look at those. 1s2, 2s2, 2p6, 3s2. Again, these are very simplified, but they're giving us a really nice way to conceptualize it, and it's very accurate in terms of the meaning of looking for patterns. So if you're right next to the nucleus, you can see down here on the bottom, then you're experiencing a 12 plus charge. But there's 2 electrons on this ring, and those electrons are blocking part of the charge. So if you're on the second ring, if you're on the 2s set of orbitals, you're only experiencing a 10 plus charge. So you're experiencing a weaker magnet. If you go out another ring farther, there's another 2 electrons in the way right here. And so you subtract those 2 electrons from the charge of 10, and this third ring is only experiencing 8. It's only experiencing a magnet of 8. And there's 6 electrons on this ring, and they're interfering with that nuclear charge. So we subtract those 6 electrons to find out that our little 3s electrons are only experiencing a magnet of 2 plus. That's just not really that strong. And that's why it's so, well, it's easier to take these guys on the outside, and then it gets much harder to take the electrons in the 2p6 because their magnet they experience is 8. The 3s2, they only experience a magnet of 2, and they're like, it's not that strong. They might encounter another magnet that is stronger, like a fluorine or something like that. Fluorine would just snatch those little guys up from that 3s2 orbital. Absolutely no shame. Just steal them. Okay, let's look at another example real quick just to compare. Let's look at sodium. This is magnesium's next door neighbor. Its magnet is only 11, but it has the same basic orbital structure because it has 1s2, 2s2, 2p6, and then it ends in 3s1 because it only has 11 electrons. So the ones close to the nucleus experience 11. There's 2 of them, and they block part of that charge. So the second ring, 2s2, only experiences 9. And that blocks even more of the charge. So 9 minus those 2 electrons gives us 7 experienced by the 2p6. And the 2p6 has 6. And so now the 3s1 is only experiencing a magnet of 1. So that's super easy for somebody to come pick off, right? They can take that electron, no problemo, because that's not a strong magnet that's holding on to it. It's got all the shielding in the way, plus it's all by itself out there, so it's just kind of awkward. So if sodium gets rid of that, then it has that 2p6, it's experiencing a magnet of 7, it's got a full octet, and then sodium's really stable. So that's why when we look at sodium and we put it in water, metallic sodium just goes crazy trying to get rid of its 3s1 electron because the magnet is just not that strong, and it's like, dang, if I got rid of this awkward little electron that's out all by itself, I could have a full octet. That's pretty slick if you're a sodium. That's what you want to do. So here's a picture. I've drawn our little electron friends back in just to give us another aspect of the visual. You can see this little guy sitting by himself experiencing the +1. These guys are experiencing the +2. And so you can see why it's going to be easier to take from sodium than it is to take from magnesium, because magnesium has a stronger magnet. And they're kind of experiencing the same shielding. And once you get to that second ring, the +8 and the +7, they're both kind of a lot more difficult to take from at that point. But you can see how the whole time the stronger magnet of magnesium is making it a little bit harder to take the electrons away. So we're going to go ahead and go back to thinking about the overall trends of ionization energy on the periodic table, but we will do that in the next video because the free video recorder I'm using is out of time.